Excuse me. Alright, so my name is Bradley Champagne for Group 1, and next week Group 1 is going to take their shot at doing the bomb calorimetry. And so now what Alexander Douglas was saying about bomb calorimetry, it's the quantification of heat, the number of heat units that are liberated whenever a fuel sample is burned, whenever it is ignited. Now, some people may ask, like, what is the point of this? Like, why do we do bomb calorimetry? And the purpose from an engineering standpoint is to know how much heat is released whenever we want to look at endpoints from a thermodynamic standpoint. Because whenever we have a heat, we can specifically calculate a delta T, and some things are actually very useful, like a delta T, whenever you want to know how much temperature you need in order to change something, whenever you want to change the quality of a fluid or even a solid object. Okay, so that was the theory behind it, and the equations that we use for this are very simple. Okay, we have an overall thermal capacity, which is actually the mass times the specific, which will quantify it to just an amount of energy per a unit of mass for an object. Okay. Now this is just a basic picture of the setup of the bomb unit itself. So this right here is a thermocouple that's going to measure the temperature change of the water. In the process, we have this stir that's going to promote as uniform as possible a temperature distribution of the water. Okay, because any temperature gradients could give inaccurate results of the change in temperature. Now, this big outside shell is a big insulator. This is to minimize the amount of heat that we just lose out, okay? Because this would cause an error. This would cause errors in our final calculations. Which, by the way, since we have things besides the bomb unit in the water that will absorb heat, we're going to have errors anyway. But to calculate the heat of these devices, as I researched if it was possible, I unfortunately came to the conclusion that it's pretty awkward and these can actually be neglected. Now, over here, this is a smaller picture of the actual stainless steel container that's going to contain the fuel. And this, you can see this little square here is the benzoic acid tablet that Alex was talking about. These are the ignition wires. And again, this is stainless steel, okay? Now, there's two different stainless steels, and what I did in my subsequent calculations for an example is actually looked up the heat value for that. So the basic setup is to actually use the stainless steel cup itself, load a tablet, and establish the circuitry. I know it's kind of general for the purposes of the lead rule. But the purpose is to ignite the fuel sample, okay? And this is a constant volume calorimeter because we're just going to keep everything, the whole ignition process within an enclosed volume, okay? It's not like a coffee cup calorimeter where it's not sealed very well and it's open to the atmosphere. Okay? So some people ask, why do we use 2 kilograms of water? Like, why not more or why not less? In my opinion, it's really just because it's a known quantity. It's just a standard practice number. It's something that we can easily quantify. So we assemble the bomb, quote-unquote, bomb unit in itself inside the shell, establish the water seal, and then eventually we will seal up the unit for it, the outside bucket. Forgot the name of it. The insulator. Thank you. And pretty much get to work. Now, this is supposed to be like the ignition itself is supposed to take like 2 seconds or so. The calculations go is, again, as Alexander Douglas said, it's a very simple process. We use quantified numbers that we know or we can easily look up. So one of the things that we can do, one of the goals actually of this is to, what I should have said earlier, is to actually get an overall heat capacity of the calorimeter itself. Okay, because there's some that we know, like water, sure, benzoic acid we can look up, sure. But we want an overall capacity for the calorimeter itself. And with that, we can calculate the heat out of any unknown source, okay? So for a general one, this isn't the calibration version that Alexander Douglas was talking about. This is an estimation quantity that you can use. From this, okay, because see, like you can see stainless steel here that I used, and a mass was given, so I was able to look that up, and I'll cite that at the end. But I was able to get that value from doing this simple calculation. This here was another looked up value for the benzoic acid itself. It's a heat value. It's an amount of energy per unit mass. Okay, and I was able to use this known value and this actual calculated value from an example, and I got roughly a pretty similar temperature to what Alexander got. And again, from this, you can calculate any heat liberate that you get from any fuel. So those are my references. Does anybody have any questions?
Which stainless steel did you go with?
I went with 430 stainless steel. What was the value for that? I think it's still on my calculator. I want to say it was like 406-ish joules per kilogram, but I used kilogram units instead.
I got you. I used the opposite ones.
You used 304?
Yeah. I used the higher one.
Yeah. Anybody else?